So in this lecture, we will start our study of trajectory planning. Okay. So what is the task in trajectory planning? We have to understand, and how to do it. We will see how that is done. Okay. So yes. So as the problem of trajectory planning goes, the situation is that you need your manipulator hand to move from one location, one position and orientation to another position and orientation within a specified duration, within a specified time. Okay. So given the transformation matrix capital T at the initial time and the transformation matrix at the final time, you need to find out continuous sequence of transformation matrices through which the manipulator hand has to go from the initial pose to the final pose. This is the plan. Okay. Now, one important aspect of this is that you need to actually develop the intended time history of the motion of the entire manipulator, because you need to plan the motion of the entire manipulator, without which the hand on its own cannot go. Okay. So what are the aspects that are important here? Most of these are common sense. So you need continuous motion because the manipulator cannot jump from one configuration to another. So continuous motion required, and smooth motion would be preferred. What is the meaning of continuous and smooth? The sequence that you work out, they are one after the other close by. That is, only small rigid body motions are needed from moving from one pose to the next pose in the sequence. That is continuous. Okay. Not only that, if you want that continuity, not only continuity but differentiability, that is the rate also changes slowly, then you say it is smooth. Okay. So what order of continuity? If you want only positions to be continuous function of time, then you say continuous. Then one derivative, if you want continuous, then you say differentiable. And the second derivative continuous would actually give a motion which is smooth. Okay. So up to what you would get, that depends on the purpose, accuracy required, and so on. Okay. Then basically the point is that you want your end effector to move. That means the end effector coordinates capital X, X, Y, Z, alpha, beta, gamma, those things, or simply the transformation matrix. That is what your intention is. But you can give actuations only at the joints. Okay. So you need to give actuations here to bring about an appropriate change here or here, which is the same. Okay. And you know that this mapping is nonlinear. So if you want a specific kind of motion, specific kind of sequence here, and a similar kind of sequence you apply on the joint variables, then that would not operate because this mapping is highly nonlinear. So this is another thing that you have to keep in mind. Further, as the robot hand moves from one position to another, it is extremely important to ensure that the robot hand or any other part of the body, any of the links of the manipulator does not collide with any of the objects around. So that problem you call obstacle avoidance. Now, the real big issue of obstacle avoidance is studied not in trajectory planning, but in robot motion planning, which is a much more complicated area. And there you, for handling that complicated problem, obstacle avoidance, you may not bother about description in terms of time. As long as you get a collision-free path, you are happy. After that, that path, whenever to be implemented, can be always reparameterized in terms of time. Okay. So, however, it may happen that your manipulator and your objects around are quite sparsely structured. So, collision is not a big possibility. So, in that case, you may not at all do robot motion planning if your workspace is more or less free. So, whatever motion you plan, you typically expect it to be collision free. Okay, and through simulation, you will take one route. So, categorically, motion planning you would do in those cases where you know that your workspace is cluttered and there are several possibilities of collisions here and there, and you have to carefully avoid it. Now, suppose your arena is more or less free and you are not doing that obstacle avoidance separately. Still, some obstacles would be there on the way which you must avoid. For that matter, the table on which the tool is lying, from where the robot hand is supposed to pick up the tool, that table is actually one obstacle. Typically, when we human beings pick up an object from the table, the chance of our hand or our legs colliding with the table is minimal. Normally, that doesn't happen. Okay, but we already discussed that this point motion to task space motion is nonlinear mapping. So it may happen that you are moving your joints in a sensible manner, but the in the task space it is moving a little on the wrong direction first. So, for example, if it has not been already carefully planned, then it may happen that rather than picking up an object from a table and going away, the first round of action after the pickup might be to dig into the table a little, which should not be allowed, right? So that is one big possibility of hitting something inadvertently. Okay, that is by wrong planning. Here there is no, human intention. Here it is all programmed. Human intention is to be programmed into it. Another place where a possibility of hitting something is high is where the tool is supposed to go. Okay, because at that point where the tool is supposed to reach finally, the T final, the transformation matrix final, where it is supposed to do something or put it somewhere. If it is not a tool, if it is a thing, object which has to be transported somewhere, so there it has to deliver it. Just around the time of delivering, if it tries to hit the pin first and then deliver, or while going with a wrench, if it first hits the bolt and then tries to hold it, that will be a problem. So there also an obstacle avoidance problem is there implicit, even if there is no sense in hitting it, because of this non-linearity of the joint space to task space mapping. That danger is there. So these two you must avoid. Besides, if the arena is more or less free, but there is something in between which might hamper the motion of the hand or the rest of the robot, then you might need to avoid that object. So in order to handle these things, typically people use the so-called via points. So rather than mentioning only the initial transformation and final transformation, you might also mention some transformations in between, basically in order to guide it properly. Okay, we will again come to the issue of Wire points later. And why we all do all these? Because inverse kinematics of manipulators, the kind of manipulators that we normally use, is computationally much more costly than direct kinematics. So the intention, our idea, therefore, is typically to plan the motion of the joints and get a suitable, acceptable plan at the end effector in the task space. Okay. So, and that is why all this non-linearity of the mapping is involved, because even otherwise it would be involved for the body of the robot, for the links, not just the hand. Okay. And so you cannot do it like this, that from first initial transformation to final transformation, you work out a sequence of 200 transformations and then say at time equal to this, time equal to this, time equal to this, time equal to this, I want the robot hand to be at this transformation, this transformation, this transformation, this transformation, and so on. You cannot say that, because if you say that, I mean, you should not say that. You cannot say that. You would like to avoid saying that, because in that case, at 200 transformation matrices, for 200 transformation matrices, you will have to do inverse kinematics. Okay. The smarter thing to do could be to transform the initial and final and a few configurations in between, a few poses in between, which you are providing for guidance, that is via points, and then say that from this time to this time, let it reach from here to here by whatever joint motions. Okay, and then actually plan the path in joint motion, which anyway reaches there. So that is the idea. Okay. So typical solution is point space schemes in which you do inverse kinematics for the initial transformation, the final transformations, and the in between via point transformations. You can say that at time 0 it should start from this pose, at time 20 seconds it should reach this pose, and on the way at 2 seconds, 12 seconds, and 18 seconds, let it reach these three prescribed poses, T1, T2, T3. T1 so that it does not hit the table from which it is lifting the object, and T2 so that it does not hit something in between, and T3 perhaps so that it does not hit the bin where the robot is supposed to deposit the object. I mean, it could be more, or it could be less. So then you have these time instants and you have these corresponding theta positions. 6 theta values, or as many degrees of freedom you have, that many joint variable values at initial time, at time t1, at time t2, and so on, and then at final time. That means these many times, a plus 2 times, you have done the inverse position kinematics. And that much computation you are ready to handle. And then the business boils down to planning a motion from here to here, here to here, here to here, and so on. Okay, and this motion should be continuous, preferably smooth. Now, planning a continuous motion from here to here is nothing. It's very easy. It's an interpolation, and you will get a continuous function. Planning from here to here is also straightforward, equally simple. Another continuous motion. The point is to ensure continuity across this. then across this, then across next, and so on. And at initial and final, whatever is the position, velocity, acceleration that is demanded. Okay, so that across points ensuring the continuity is the big issue. Okay? So when you do this continuous and smooth, continuous or smooth interpolation to get these things as function of time, basically you need theta 1 running from initial time to final time as a function of time, theta 2 also as a function of time, and you are doing it segment wise from initial time to t1, t1 to t2, and so on, and separate arrangement or caution has to be exercised to ensure continuity across these. Okay? Because planning one segment continuous is very easy. Okay? And then after smooth interpolation, you have got theta t from theta of t from initial time to the final time, and these 200 joint positions, theta vectors, 200 theta vectors, you can transform to the end effector side to get the actual path by direct position kinematics. So we avoided doing inverse kinematics at 200 poses and did quite a few other things in between, and finally we are landed at direct position at 200 theta values. That is, we will do 200 direct kinematics problems rather than 200 inverse position kinematics problems, because direct kinematics in these manipulators are quite straightforward and the solution always exists, it's always unique, and it is, continuous at least. Okay. So that is the advantage of this kind of plan. So this is a typical way robot motions are planned and executed. This is how typically trajectories are planned. We will see the details. And through this direct kinematics, you verify the acceptability of the motion that you have planned. Because after this direct kinematics, now you are going to really get the check whether from here to here the robot, any part of the robot hit anything or not. From here to here, whether it is fine, okay, and so on. So all these checks now you are going to get through this direct kinematics, and that is the purpose of this direct kinematics, because otherwise you could give the joint motion and you could expect the direct kinematics to play itself out on the robot body itself. But no, you want to do it beforehand to get this sequence of the transformation matrices as function of time and verify through simulation that nothing goes wrong. Okay? So now the problem boils down to how to plan each and every segment here and how to ensure continuity between them. Okay? And one point you must have noted already, that after you converted the transformation matrices at via points from the task space to the corresponding theta values, then actually the entire problem got decoupled. Originally the plan was needed for at the transformation level, that which is the result of all the joints of the manipulator. But now that you have converted it into the joint variables, now how different joint values are going to change from this set to this set and this set to the next set doesn't matter. So if we decide that for going from Kolkata to Delhi, we as a party will meet at places in between to secure that everything is all right. So we'll meet at Patna, we'll meet at Allahabad, we will meet at Kanpur, and then at Delhi. So Then between Kolkata and Patna, between Patna and Allahabad, how you are going and how I am going doesn't matter, if all of us can meet at those pre-decided junction points. Okay, so for the planning of each of them, as long as they satisfy the correct time, correct position of their own joint value, we don't care for the others. And that is how the complete coupled problem actually gets decoupled into 6 parallel strands of similar problems. And that similar problem, ensuring continuity for each of them separately, is what we will have here. What the kinds of joint space schemes that the trajectory planning of manipulators typically use. However, this will take a lot of detailed work, and I want to handle this at a proper pace later. Before that, the conceptual issues of this topic we cover right now. Till now, we have discussed ideas of avoiding planning the motion in task space, avoiding to plan in terms of transformation matrices or task space end effector coordinates, to do it in joint space. However, there are some situations where task space scheme may be necessary for specific tool motion being demanded. For example, if the current task for your robot, for your manipulator, is just to take an object and deposit it somewhere, then you may say that through what path the hand is moving, we don't care, as long as on the way nobody hits anybody. Okay, the hand or the tool or any of the links of the manipulator does not hit anybody else in the environment or other links. Okay, and then it deposits the object at the right place at the right time, then we are happy. If that is the task. On the other hand, it may happen that the task is to execute a welding along a particular path. Okay. See, if it is spot welding, that your robot has to weld at these 8 spots, then you could still manage it. You could say that go from 1 to 2, do the task, and 2 to 3, do the task, and so on. But if it is, welding on a curve continuously, continuous welding, then the tool has to follow a certain path. You cannot say that start from here and go whatever way you want. And in such situations, a specific tool motion may be demanded, and the hand has to take the tool through that path, and that means the hand has to move over that path. And in that case, you have to plan in a task space scheme. Okay? Then you have to accept the higher computational load, do all the necessary inverse kinematics and so on, and you have to bother about too many extra things also. If you plan a motion, say you say that I want a straight line motion, okay, then because the welding path is straight line, okay, then you have to bother that just commanding that let the hand move here along a straight line, 100 poses along a straight line. But some of them may not be possible because for inverse kinematics, solutions may not exist. So non-existence of intermediate solution. You cannot just offhand say that do this. In the case of the joint based planning, you could have done it because you knew that this particular joint can move from minus 120 degree to plus 140 degree or 0 to 360 full circle. Then within that range, whatever it is the range of that particular joint. You could say that whatever motion is in this joint, we accept it. Okay? Now here you cannot say that, because here it's a complete coupled problem, and there may not be any joint position that gives you a specific intermediate solution for the end effector. So this requires heavy work in the background offline beforehand. Okay. Then for every configuration of the hand, there may be 2 or 4 assembly configurations of the manipulator. So the joint positions may be multiple. Okay. We have seen that inverse position kinematics may have 4 solutions, 8 solutions. Okay. So then the question is, you have to choose one of the branches. Now it may be that any of the branches is acceptable. Okay, but you have to choose it. So to a human being, you can say, let's take any of the ways. But to a robot, you have to tell, because it is a computerized system. So even if both choices are acceptable, you need to tell it that pick this or pick that, and in that case, you have to characterize it, or you have to tell that out of the 2 choices that you have, generate a random number, either positive or negative, and take this. If it is positive, take that. If it is negative, some logic you have to give. Okay. So to a boy, to a human being, you don't have to say that whether to take left or right turn. Whichever you take, you reach the same destination. But how to decide which one to take? So toss a coin. You don't have to toss a coin. You don't have to tell him to toss a coin. But here, even that you may have to tell. Okay, even that, if that is the idea. So out of the multiplicity of the solutions, you have to specify clear-cut rules how to select one. And it will be nice if you can select at every point that one out of the possible branches, which gives rise to less possibility of this at later places. Okay. Then we saw singularities. Okay. So those points which are at near singular configurations, there for small motion at the end effector, the joint motion may be enormously high. We have seen that aspect of singularities. So in task space schemes, you have to specifically separately ensure that such singular configurations are avoided, singular neighborhoods are avoided. Okay, branch defect is actually this only. And either you have to have high storage in your system from where you drive the robot, or you have to take up a lot of real-time computation. How you avoid real-time computation with high storage? At real time, rather than doing so many inverse kinematics problems, you may say that what about I do the inverse kinematics beforehand and store the theta values somewhere. So you will then need high storage. Typically, I would advise that it is a good idea to do the computation offline, verify everything, and for every pose of the end effector that you plan in the task space trajectory scheme, for each of them you do inverse kinematics, whether it is 200 or 700 or 2000, and all those theta 1, theta 2, theta 3, theta 4, theta 5, theta 6 values as functions of time, you go on putting in a table. And that table, that large table, some 2 MB table perhaps, 2 megabyte table, you keep in the storage, in the disk of the system from where you are going to drive the robot. And then in the basic program, you can simply say that at every time instant, look up that table, and against that time in the next row, whatever are the theta 1, theta 2, theta 3 values there, you use them. On the way, you will need, digital to analog converter and so on. So those things are hardware based issues. So that is one possibility of handling this kind of a situation. Okay. So these are the conceptual issues that we needed to understand and appreciate while or before doing trajectory planning. And the major task that is mostly practiced in industrial robotics, that is joint space schemes, the nitty-gritty of it, the details of it, what kind of schemes we use in joint space for most of the planning purposes, and how we ensure continuities across the via points or at the endpoints, that we will discuss in the next lecture. And in this current lecture, there is another conceptual issue that I need to repeat again. At the runtime, when the robot actually executes, when it operates, then actually the trajectory needs to be generated at online time, runtime, either from the entire calculation. In the case of joint space schemes, that may be quite straightforward as long as the rules are already there. In the task space table, that may be computationally costly, so you can do through lookup table. This is one thing. And the other is that we are still leaving out an enormous segment of related issues of path planning or motion planning, which the focus of which is primarily collision avoidance. In fact, motion planning is a huge area, and in IIT Kanpur we have a separate course on robot motion planning. But in this course, we give a little sample of the basic ideas of robot motion planning. In my original plan, I had robot motion planning listed in the course plan immediately after trajectory planning. Okay, but my partner, your other instructor, Professor Datta, pointed out that motion planning is better handled in the context of programming, because therein comes in proper context, and so we have shifted it there, and it has been decided that he will handle it, okay, when he comes to programming. So one important point you should note that this motion planning through collision avoidance, this business is to be handled primarily for the geometric path of it, and not with a lot of issues with time. And trajectory planning is necessarily parameterization with respect to time. And the motion planning is collision avoidance business, separate programming you may or may not do. On the other hand, trajectory planning is something that you have to do for every robotic operation. That is the second thing. And the third thing is that even if you do the formal motion planning for collision avoidance, the path that you get from there, that is only a sequence of configurations or sequence of positions that anyway needs to be reparameterized with respect to time, and that will be then the limited task of the trajectory planning in that kind of a situation. So trajectory planning is the basic problem which has to be solved always, and in more complicated situations, the more advanced problem of motion planning, path planning through collision avoidance also needs to be handled. Okay? So keep this much in your head right now, and in the next lecture, we will see the details of the joint space planning. Okay.